doesn't it? On the left, you've got the ENIAC computer from 1946. This absolute monster had 20,000 vacuum tubes, and yeah, it filled a whole room. Then on the right, from just 30 years later, you have the Intel 8085 microprocessor. The change in scale is it's mind-blowing. So how on earth did that happen?
Well, this incredible shrinking act wasn't some kind of magic trick. It all came down to a couple of revolutionary breakthroughs that completely changed the game for electronics and really created the world we live in today.
Okay, so it all kicked off in 1947. That's when we got the transistor. This tiny little switch replaced those huge, clunky, and honestly super unreliable vacuum tubes. Then, a little over a decade later, in 1959, the integrated circuit came along. Suddenly, engineers could cram a whole bunch of transistors onto one tiny piece of silicon. And that, right there, set the stage for the very first microprocessor in 1971.
And you can really see how quickly things started to snowball here. In the early 60s, we were at what's called small-scale integration, or SSI, packing maybe a few dozen devices onto a chip. By the 70s, we hit large-scale integration, or LSI, and we're talking thousands of devices. And today? Today, with ultra-large-scale integration, we're talking billions, with a B. This kind of insane growth needed a name.
And that's where something called Moore's Law comes in. Gordon Moore, one of the founders of Intel, noticed this trend back in 1965. Now, this wasn't some law of physics, it was an observation, a prediction really, but it was so accurate that it became the roadmap for the entire industry, a target everyone was aiming for. It pretty much became a self-fulfilling prophecy.
And wow, you can really see it right here. This chart is Moore's Law made visible. You've got the transistor count for Intel chips, starting with the little 4004 and going all the way up to the Pentium 4. I mean, look at that curve just take off. That is that relentless exponential growth we're talking about right there in black and white.
So what's the big takeaway from all this? You take the transistor, you put it on an integrated circuit, you ride that crazy wave of Moore's Law, and what do you get? You get the ability to put an entire central processing unit, the whole brain of a computer, onto one single tiny chip. And that was the birth of the microprocessor.
And you'd think this world-changing invention was designed for some, top-secret government project, right? Nope. Its first job was to be the brain of a calculator. Just goes to show you, sometimes the biggest revolutions have the most humble beginnings.
So, to really get our hands dirty and understand how these things tick, we're going to pick one apart. And we're going with a real classic, the Intel 8085. It came out in 1976, and it's a perfect window into the technology of this really exciting time. And here it is, in all its 40-pin glory. What you're looking at is a complete 8-bit computer brain on a chip. This little guy was a huge deal. It was the engine behind countless devices in the late 70s and early 80s, and it absolutely laid the groundwork for the personal computer revolution that was just around the corner. All right, let's talk numbers for a sec. What are we dealing with here? Well, it's an 8-bit processor. That just means it works with data in 8-bit chunks, or 1 byte. It could talk to 64 kilobytes of memory, and trust me, back then, that felt like a ton of room. And it chugged along at 3 megahertz. Sounds slow now, but it was flying at the time.
Okay, so now it's time to pop the hood and take a look inside. And what's really cool is that the basic building blocks we're about to see aren't just in the 8085. They're in virtually every CPU ever made, including the one in your phone right now.
So at its heart, any CPU is really just 3 main sections working together. First, you've got the control unit. Think of it as the project manager, or maybe the traffic cop, telling everything else what to do and when. Then you've got registers. This is like the CPU's own super fast little scratch pad for holding on to the data it's working with right this second. And finally, you have the part that does all the heavy lifting, the arithmetic logic unit, or ALU.
The ALU, yeah, this is where the magic really happens. It's the number cruncher. It's the mathematical brain of the whole operation. Every single time your computer adds 2 numbers or subtracts one from another or compares 2 things, it's the ALU that's doing that work.
Okay, so you have all these different parts inside the chip. That's great. But how do they all talk to each other? Well, the answer is something called a bus system. And honestly, the information highway analogy is perfect. It's the road network that connects everything. So what is a bus, really? It's just a set of tiny electrical pathways, little wires basically, that connect the CPU to memory and all the other parts of the computer. It's how the CPU sends and receives everything: data, addresses, control signals, you name it. Now, this is where the engineers designing the 8085 hit a bit of a snag. A puzzle, really. They had a ton of information they needed to move around. They needed 16 separate lines just for addresses and another 8 for data. But they only had 40 of those little metal legs or pins on the outside of the chip to do it all with. So, how'd they squeeze it all in?
The solution was seriously clever. It's a technique called multiplexing. Basically, instead of having a dedicated lane on the highway for every single car, they decided to have some lanes that could be used by different kinds of traffic at different times. They made 8 of the pins pull double duty. One moment they're carrying an address, and the next moment they're carrying data. Okay, this diagram shows us the trick. See the 8085 on the left? You've got some pins at the top that are only for addresses. But then you have this group at the bottom, the AD0 to AD7 lines that are shared. The secret sauce is that little component in the middle. It's called a latch, and it's the key to the whole operation.
So here's how it works, and it all happens incredibly fast. First, the CPU puts the first part of a memory address onto those shared wires. Then, a special signal called Address Latch Enable, or ALE, gives a little pulse. It's basically shouting, "Hey latch, grab what's on the wires right now." The latch does its job and holds on to that address information. And just like that, those exact same wires are now totally free to carry data. It's this beautifully timed little dance.
So what's the bottom line here? It's pretty simple. This whole multiplexing trick meant they saved pins. And saving pins meant a smaller chip, a cheaper chip, and a simpler circuit board for it to live on. It was a really elegant solution that was absolutely key to making this stuff affordable and practical.
And let's just step back for a second. That whole system we just described, the brain, the scratch pad, that clever highway system, all of it was built from about 6,500 transistors. For 1976, that was just incredible.
And that just brings it all full circle, doesn't it? We've gone from the 6,500 transistors in the 8085 to literally billions of them in the device you're using to watch this right now. The scale of progress is almost impossible to wrap your head around. It just leaves you with one big question. If this is what we did in the last 50 years, just imagine what's coming in the next 50.